There are a couple more definitions that will become useful later. The first is, what if we don't care so much about what is the specific hypothesis about the world that exists? What if we just want to know uh, what to expect to see in the future? For example, uh, we don't necessarily care what the rule is. We just want to know which numbers we should expect are part of our concept. Or if we're doing this number learning game in the context of, let's say, a course, which numbers, if I tell my teacher are part of the concept, are likely to be correct. We use the same thing when it comes to, let's say, a machine learning classification problem. In that case, our data values are pairs of image and label, like photo and dog. So what we're really doing is we don't necessarily care what the underlying rule is that decides whether or not a photo is a picture of a dog or not. What we care about is, if I see a new photo, is that a dog or is it not a dog? So we can do this as follows. We want to know what is the probability of y, that is a specific data observation that we might see in the future, given all the data that we've seen so far, that is y1, y2, y3, and so on. Notice that the hypothesis doesn't appear anywhere here, because again, we don't actually care when making this prediction which model we choose. So we can, if we kind of think about this this expression, we can realize that it equals the following: the sum over all the possible h's of probability of y given h times probability of h given d. Okay, so why is this correct? So we're using here the following identity. The probability of A is equal to, I can always sum over some other random variable. Here I'm summing over the possible values of B, probability of A and B equals small b. So again, I'm summing over all the possible values of this small b. So one way to convince yourself that this is right is to draw something like this. Again, here I'm showing the black box is all of the possible worlds we could live in. Here I'm dividing it by the possible values of b. So b could equal 1, could equal 2, could equal 3, could equal 4. And then a has some probability of occurring if b equals each one of these values. So maybe it's higher if b equals 2 and lower if b equals 1 or whatever. But in any case, if we take the probability of A and B1 plus the probability of A and B2, probability of A and B3, and so on, and add those all together, what we get is the total probability of A. So that's a handy identity. So let's apply that here. Here we have, we're using an identity to sum over H. By the way, here's a bit of an overloading of notation again. Notice that I have here H all by itself. We're implicitly writing here all the possible H's within the larger hypothesis at big H, but we're just omitting the within big H because that's implied. So again, here I have probability of y given d. Now I'm just adding in H, probability of y and H given d, just applying that identity. Now I'm going to apply the chain rule to this expression here. This is probability of H given D times probability of Y given HD. You can just see that that's that same conditional probability rule we've used a bunch of times. And now notice that Y, if we know which hypothesis is correct, then the data doesn't tell us anything in addition. The data was just there to tell us which hypothesis was correct. So that is not involved. So then we get this expression here. So that was a long way of saying that if we want to know what is the probability of a given observation, we can compute it like this. We have to sum over all of the possible hypotheses that we could imagine happening. So this is something we could do. So if we want to know what numbers to expect in the future, given, let's say, that we've seen 16, a reasonable thing to do, and probably the thing we would do intuitively as humans, would be to think about all the different rules that could have produced 16, think about what posterior probability, that is this here, we apply to each of those rules, and then ask what is the probability of each number we could see in the future given that rule, and we add them all together. That's called the posterior predictive distribution. And again, this is used anytime we want to know what observations to expect in the future given the data we've seen in the past. A couple more definitions that will be useful. The first is we define the map hypothesis, that is the maximum a posteriori hypothesis, as whatever hypothesis has the highest probability. So if we want to pick a specific rule and say this is the rule that I think is going on, the right rule to pick would be the maximum a posteriori rule. Another thing that's useful to define is the MLE, the maximum likelihood estimate hypothesis. That's just the hypothesis with the highest likelihood. Notice here I have D given H, which is that what I'm showing here is the likelihood of H, as opposed to here that I'm showing the posterior. Now, a thing to realize is that the posterior is proportional to the likelihood times the prior. So another way to think about the maximum likelihood estimate is it's just the hypothesis we would get for our MAP, maximum a posteriori hypothesis, if we ignore the prior or use a prior that's equal for all the different hypotheses. Now, something that's done very often in practice. I told you on the last slide that if you want to know the posterior predictive distribution, again, that's the probability of some future observation given everything we've observed so far, I told you that you have to sum over all of the hypotheses that you could imagine. Now, that is computationally challenging, so something that's done very often in practice, and in fact for most machine learning applications, I say, well, this posterior distribution, let's just pretend that all of the probability is on whatever the maximum one is. This is, we're defining H hat as the H map. Or it could be some other single point hypothesis that is a specific hypothesis that we pick some other way, perhaps by the MLE. We say, let's just pretend that all of the posterior is on that one. And then I say the probability of y given d is roughly equal to the probability of y given that specific hypothesis. So we do that usually in machine learning instead of keeping track of all the different models and assigning a posterior probability to each one. Usually we do some learning and then from that form a posterior distribution and pick whatever the best model is and use that for our future predictions. So realize that choice of picking a single model or a single hypothesis, or in the case of a number game, a single set of numbers, and using that for our future predictions, that is a common thing to do, but it's not a fully rigorous thing to do. It doesn't fully respect the uncertainty we have about the problem. Okay, that's the end for our section on concept learning. I'll see you in the next lecture.